This is chapter 10, section 3, talking about Taylor series. So there's not really anything new here. It's more just definitions and things to think about. So we're just going to do some examples, and that's it. So we've been talking about power series. So this is the general form of the Taylor series. So we're going to be centered at A, and you already know this, but before we did Taylor polynomial, where we only took a certain amount of terms, this is an infinite series. So it's the same formula, f of A, then we take the derivative at A over x minus A, and if you want, you could put a 1 factorial down here and a 0 factorial here to fit the pattern. But this is a very familiar formula for you, and here's the general term. Right here, you should be comfortable with summation notation. If not, you need to spend some time thinking about that. Now here's a definition for you. So this is a form of a Taylor series. If your center is at 0, in other words, if A is 0, it has a specific name, and that specific name is a Mclaren series or Mclaren series. So if you hear Mclaren series, it just implies that the center is at 0. So here's our first example. We're going to find the Mclaren series for two functions, and we're just going to build this the old-fashioned way. We're just going to take the derivatives. The center we know is going to be at 0, and we're just going to build it. So let's do this. All right, so in order to build it, we need derivatives. So let's just start doing this. F prime of x is minus sine x. F double prime of x is going to be minus cos x. F triple prime is going to be sine x. And we'll go to the fourth derivative. I think by that time we'll see a pattern. Let me do a couple more. We're good. Minus sine x. And we'll go up to the sixth derivative. Now we are centered at 0. When it says Mclaren series, you know A is 0. So we need f prime at 0. Well, sine of 0 is 0. We need f double prime of 0. Cosine of 0 is 1, so it's going to be negative 1. And then, that's bothering me for some reason. Oh, it's not. I know why. We need f of 0. So cosine of 0 is 1. And let's continue down this pattern. This will be 0 because sine of 0 is 0. The fourth derivative, cosine of 0 is 1. The sixth or fifth derivative, sine of 0 is 0. And then the sixth derivative at 0, cosine of 0 is 1, but there's a negative, so that's our pattern. So let's build this. Can I copy and paste? I'll just write it out. And we have to find the interval of convergence, so I might have to do some erasing, but we're good. So it's going to be f of 0 plus f prime of 0 x plus f double prime 0 x squared over 2 factorial, f triple prime 0 x cubed over 3 factorial, and then the fourth derivative times x to the fourth over 4 factorial. I'll go all the way to 6. The fifth derivative is 0, x to the fifth over 5 factorial, and then the sixth derivative at 0, x to the 6 over 6 factorial. And let's see if we can get a pattern for this. So taking the values from above, we got 1, 0, negative 1, 0, 1, 0, negative 1. So 1, 0, negative 1, 0, positive 1, 0, and negative 1. And this continues, so here we go. It's 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial plus dot, dot, dot. What is the general term? If you look, it looks like x to the 2n over 2n factorial. And let's try this. Plug in a 0 here and a 0 here, and you will get 1. Plug a 1 here and a 1 here, you get x squared over 2 factorial. Oh, I need a negative 1 to get this to alternate. So it's alternating. So let's move this over here. Now, if I do a negative 1, if I just do n, let's see what happens, okay? So n is 0. That's going to be 1. We'll get that. If n is 1, you're going to get a negative 1, and you'll get x squared and 2 factorial. So it seems like it's going to work. If n is 2, that'll be positive. This will be 4. That'll be 4. So this looks like this pattern works. And then in summation notation, k equals 0 to infinity, and it's going to be negative 1 to the k, x to the 2k over 2k factorial. And to double check, just plug in your 0, and you should get the first term. Plug in 1, you should get the second term, and I think we're good. So this is the Mclaren series for cosine x. And we could do this for sine, we could do this for e to the x, we can do it for a lot of things. This is one that you will have memorized in due time. All right, but we're not done. They want the interval of convergence. So looking at the fact we have factorials and exponents, we are going to use the ratio test. So R is the limit as k goes to infinity, and it's absolute convergence. So we add k plus 1, or add 1 to all the k's. And you divide that by the original, which is multiplying by the reciprocal. A few things to note. Since it's absolute value, we don't care about the negatives. And then we're going to start to simplify. This is 2k plus 2. This is 2k. That means that this one has 2 extra on top. So when you cancel those, you're going to be left with an x squared. Now if you multiply this out, this is 2k plus 2 factorial. So if you were to write this out, prior to the plus 2, you're going to get 2k plus 1. Prior to that, it's going to be 2k. And you start at 1 dot dot dot. This is 1 up to 2k. So all of that's going to cancel with that, leaving you with this. Okay? All of that's going to cancel all that. And what do we have? We have the limit as k goes to infinity. And on top, we have x squared. And on the bottom, we have 2k plus 1, 2k plus 2. And here's some weird thoughts. X squared is actually a constant. Because if you want to find like cosine of pi, you would put pi for all your x's. And therefore, in each term, that x is a constant. It's just pi. So we can take that constant out front and have the limit as k goes to infinity of 1 over 2k plus 1, 2k plus 2. But you'll notice all of this is 0. X squared times 0, which is 0. So what does that tell you? In the ratio test, if your r comes out to be less than 1, so between 0 and 1, including 0, it's convergent. So this equals 0, so it converges always. So the implication, it doesn't matter what x is. No matter what x is, this always converges. So the radius of convergence is infinity. Your interval of convergence is from negative infinity to infinity. So that is how you do the interval of convergence for the cosine function. All right, I'm going to erase this, and we're going to start over and do part B. All right, so let me just erase everything. All right, so for part B, I won't do as many terms for part B, but your idea, the process is going to be very similar. So you'll notice I'm not going to get all those 0 terms this time, so it's going to come out much nicer. Okay, so I need f prime. Whoops, let me rewrite this as 1 minus x to negative 1. So taking the derivative is going to be easier. F prime, I bring the negative 1 in front, box, I subtract 1 from the exponent, times the derivative of box. So this is just going to be 1 minus x to the negative 2. And then the second derivative, I bring the negative 2 in front, box, to the negative 3 power, times the derivative of the box, which is negative 1. So I'm going to get 2, 1 minus x to the negative 3. And then I take the third derivative, and I bring the negative 3 in front, box, to the negative 4 power, times the derivative of the box. So the two negatives will cancel, giving me 6, 1 minus x to the 4th. I'll do one more. I think you see a pattern forming. So I have 6, bring the, that's a negative, negative 4 in front, negative 4 box, subtract 1 from the exponent, so it's negative 5 times the derivative of the box, which will give me 24, 1 minus x to the 5th. So let's look at this. This is going to be 1 over 1 minus x squared. This one will be 1 over 1 minus x cubed, actually 2. Fix the top here. And this one will be 6 over 1 minus x to the 4th. And this one will be 24 over 1 minus x to the 5th. I think the pattern is pretty clear. The bottom exponent keeps increasing by 1. And the top, look at that. That is a factorial. 1 factorial, 2 factorial, 3 factorial, 4 factorial. And you can see why it's a factorial, because you keep on moving this in front. So it's 2 times 3. Then you're going to multiply by 4. Then you're going to multiply by 5. So you keep on increasing the number you multiply by. So you can see that you are getting a factorial going on there. So now it centers at 0 because it's a Mclaren series. Before. But to build Maclaurin series, here's our general form. But we need to find these values here. So in the original function, if I plug in a 0 here, I get 1 over 1. That gets me 1. In the derivative, I put a 0 here. I get 1 over 1 again. That gives me 1. In the second derivative, if I put a 0 here, I get 2 over 1, which is 2. And then in the third derivative, I put a 0 here. Whoops, that a 0 here. 6 over 1 is going to give me a 6. And then one more. For the fifth derivative, I put a 0 here. I get 24 over 1, so we get 24. But you should notice this is 0 factorial, 1 factorial, 2 factorial, 3 factorial, 4 factorial. So as we write this into our formula for the Maclaurin, that's going to be 0 factorial, which is 1, plus 1 factorial x, plus 2 factorial x squared over 2 factorial, plus 3 factorial x cubed over 3 factorial, plus dot, dot, dot. Now nicely, all these just cancel. So what does our f of x look like? We're going to get 1 plus x squared plus x cubed plus dot, dot, dot plus x to the k plus dot, dot, dot. And let me just move this over because I'm out of room again. And then the summation notation, it's k equals 0 to infinity, and it's x to the k, and you can double check by plugging those in. So we have created what we already knew for the geometric series. Now, to find the interval of convergence, now we know this is the series for the geometric. I'm not going to do the work, but we could do the ratio test like we did on the last problem, and we can find the interval of convergence just like the previous one, but not going to do that. Okay? So let's keep going through more examples. So this next example, we're going to just change the center, so it's not going to be a Mclaren series. We'll just change it to 8. So a equals 8. Our function is x to the 1/3, and so we'll just take some derivatives. That's going to be 1/3 x to the negative 2/3. Second derivative, that's going to be negative 2/9 x to the negative 5/3. And then the third derivative, it's going to be 10/27 x to the negative 8/3. I guess we can go the fourth derivative. We've got time. Negative 80 over 81 x to the negative 11/3. Okay, here's where the work begins. What's f at 8? The cube root of 8 is 2. I can do that. What's f prime of 8? So let's do this. The cube root of 8, that's going to be 2. We're going to square that to get 4, but negative puts on the bottom, so it's going to be 1/4. So 1/3 and 1/4 is 1/12. Ooh, this might get pretty ugly. So I'm going to plug in 8 into the second derivative. And ready for this. 8 here, the cube root of 8 is 2. To the 5th, wow, that's 2 times 4, 8, 16, 32. Times 2 is 64 over 9. So that's going to be 64 over 9. Is that right? Let me double check that because I'm not feeling that. I put an 8 here. The cube root is 2. Okay. 2 to the 5th. Oh, I know what's happened. Okay. I better, you know what? I better not do this in my head because weird things are happening. Negative 2/9. So I'm going to put 8, which cube root's 2. So it's 2 to the 5th, but that's going to be in the denominator because it's a negative 5. So 2 to the 5th, 2, 4, 8, 32. So that's 32. That 2 on top is going to cancel. Be 16 times 9 on the bottom. I think that's 144. Let's do one more of these because this is getting too crazy for me. Oh, and they said the first 4 terms, so if I read the instructions, I would have realized I didn't need that one. All right, here we go. Craziness. Cube root of 2, 8 is 2, but it's negative, so we're going to get 10/27, 1 over 2 to the 8th power. Now, if I were to simplify that, I would get this quite clearly because I can do that in my head, right? Wrong. I already had the answer. So let's create the Taylor series for this. So here we go. We start with f of 8 plus f prime at 8, x minus 8, plus f double prime of 8, x minus 8 squared over 2 factorial, plus f triple prime of 8, x minus 8 cubed over 3 factorial, plus dot, dot, dot. Now we just plug in the numbers we got. 2 plus 112 x minus 8 plus, oh, it's going to be minus because it's negative, minus 1 over 144 times x minus 8 squared over 2. So we could combine those and get 288. We'll do that. Plus the triple prime is 5 over 3, 4, 5, 6 times 3 factorial, which is 6, x minus 8 cubed plus dot, dot, dot. And I guess we can simplify this. I have all the answers. 2 plus, and we'll say this is our original function f of x. 2 plus x minus 8 over 12 minus x minus 8 squared over 288 plus 5x minus 8 cubed over 20,736 plus dot, dot, dot. So that's the first 4 terms of the Taylor series centered at 8 for cube root of x. All right, we have some more examples. Example 3, example 4, 2 more examples. So hang in here. Okay, find the Mclaren series for f. So this is kind of easy because, I'll show you why it's easy. F prime of x, I am my own grandpa. F double prime of x, I am my own grandpa. And it's Mclaren series, so a equals 0, so f prime of 0 is 1. F double prime of 0 is 1. And you see the pattern form, it's just always going to be 1 because I am my own grandpa. So here we go. E to the x, the Mclaren series, is going to be f at 0 plus f prime of 0 plus f double prime of 0, x. Oh, I forgot an x on the other one. Yoshida. Okay. X squared over 2 factorial plus f triple prime of 0, x cubed over 3 factorial plus dot, dot, dot. So let's do this. That's going to be 1 plus 1x plus x squared over 2 factorial plus x cubed over 3 factorial. And I think you see the pattern. It's going to be x to the k over k factorial. And in summation notation, it's 0 to infinity, x to the k over k factorial. And double check. Plug in 0. That's going to be 1. And x to the 0 is 1, so the first term is going to be 1. Let's plug in 1. X to the 1 over 1 factorial, that's just x. And you see this works. So we have found the Mclaren series for f. How do I find the interval of convergence? Again, it looks like the ratio test is a choice to make because of k powers and k factorials. So interval of convergence, r equals, and now I take the limit as k goes to infinity, and we want absolute convergence, so we'll do absolute value. We add 1 to the k. We add 1 to the k. Now we divide by the original function, which causes us to multiply by the reciprocal. Okay, let's simplify. All of those cancels with all of those, but there's 1 extra on top, leaving x. All the numbers up to k cancel with all the numbers up to k, but you have a k plus 1 left over. So here's what we have. I'm going to pull the x in front because x is a constant. And we're going to get 1 over k plus 1. But that's always 0. And anything times 0 is 0. So again, we have the same situation. It doesn't matter what x is. R is always 0. Therefore, this always converges for any x value. So the interval of convergence for this one will be negative infinity all the way to positive infinity. And so that's going to be part B, find the interval of convergence. So part C, let me erase all of this and we will get to part C. Delete. So now they want the Maclaurin series for x to the fourth times e to the x. So we're going to use that property that we learned from the last section. If I want to multiply, that's just as ugly. If I want my function multiplied by x to a power, the rule says I just multiply my series by x to that power. And it's the same series with the same interval of convergence, so that doesn't change. So what do I do to get this? I need to multiply by x to the fourth. So I'm going to multiply both sides by x to the fourth. And I'll multiply this by x to the fourth. So we get x to the fourth distributing x to the fifth, x to the sixth over 2 factorial, x to the seventh over 3 factorial, plus dot, 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 plus x to the k plus 4 over k factorial plus dot, dot, dot. And then for the summation, I bring the x inside because it's a constant, I'm allowed to. And so I have x to the fourth, x to the k over k factorial, which turns into x to the k plus 4 over k factorial. And that is the summation notation. So quite easy. And when we do those first three things, our interval of convergence doesn't change. When we integrate and take derivatives, then our radius is the same and the center is the same. We just have to check the endpoints because weird things can happen there. So that's the first one here. Let me erase all of this. And I'm going to try doing the next one using the secrets that we have learned. So I want e to the negative 2x. So I want to replace x with negative 2x. Well, we learned that's a composition and we're allowed to do that. So I can replace x with minus 2x. And I do the same thing on the right side. Every x gets replaced with a minus 2x. Every x gets replaced with a minus 2x. And we just keep going. Plus dot, 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 plus minus 2x. And then we still have the k over k factorial. And then in the summation, we replace x with minus 2k. Bam. And that's the rule. If we have a composition, we're allowed to do that. And so it's quite easy to find the Taylor series for a lot of different e to different powers, as we're seeing here. So I'm going to get 1 minus 2x plus 4x squared over 2, that will simplify, minus 8x cubed over 3 factorial plus dot, 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 plus it's negative 2 to the k, x to the k over k factorial plus dot, dot, dot. And then our summation notation, we have negative 2 to the k, or x to the k, over k factorial. All right, and that's it. Now for the interval, we know the original converges on that. We replace x with negative 2x. Whoops, that's infinity. Divide everything by negative 2, but if I do that, my inequality flips. And I'm going to get infinity, inequality flips, and infinity negative. So it's still from negative infinity to infinity, the interval of convergence. So that's that example. And then the third one, now I should have mentioned, you guys should be pausing and trying these yourself. But now we're going to replace x with that. So it's the same process. You know what? Yeah, I'll do it. I will do it. So replacing x with minus x squared. 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 All right, simplifying 1 minus x squared plus x to the 4th over 2 factorial minus x to the 6th over 3 factorial plus dot 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 plus, okay, here's where it gets weird. I need a minus 1 to the k. Then I want x to the 2k over k factorial plus dot dot dot. So I had to split this up into two separate things. It's like negative 1 times x squared to the k, so each of them get the power of k. Okay? And the last one, same thing, negative 1 to the k, x to the 2k over k factorial, and that's my summation notation form. All right, do they want also... Actually, they didn't ask for the interval of convergence for the last one, so I don't have to find the interval of convergence of that. That is my final answer for example 3. All right, let's move on to do the next one. This is my last example. So they want the first 4 terms. Then we're going to approximate 1.15 square root. And then that's it. So we're going to find the Mclaren series for this. We are going to build this from scratch. And only 4 terms. So it's 1 minus x to the 1/2 power. So this is box because it's not x. So when we take the derivative, it's going to be 1/2 box to the negative 1/2 power times derivative box. And then we move the negative 1/2 in front, decrease the power by 1, but times derivative of box. And we already have that negative 1. We have another one. So that one's already there, but derivative of box, we get another one of those. So those will cancel out in this case. Now, the last one, the third derivative, 1/2, negative 1/2, and then we're going to have negative 3/2. You move that in front, box, negative 5/2 times derivative box. So let me simplify all of these. Square root 1 minus x. This will be negative 1 over 2 radical 1 minus x. This will be, is it negative again? Negative 1 over 4 square root of 1 minus x cubed. And this is still negative. Wow. Because 2 of these will cancel. Negative. And on top, we're going to get a 3. The bottom 8. Square root 1 minus x to the 5th power. Hopefully that's right. And then it's a Maclaurin. I like that. F of 0. Put in the 0. That's easy. 1. F prime of 0. Put a 0. That's 1. Negative 1/2. F double prime 0. Put a 0 here. That's just going to be 1, and it's going to be 1, so negative 1/4. And f triple prime of 0, that's just going to be 1, negative 3/8. Now, I think there's a mistake here. That should be positive 3/8, and that should be positive 1/2. Let me double check my work. So for f prime, or actually f double prime, it should be, something's not looking right here. So the derivative, I move the half in front, decrease it by 1, and multiply by the derivative box. So my derivative should be negative. Okay, I'm kind of tripping out because, oh, I see my problem. I wrote the problem wrong. Oh well, you know what? Let's just do this. I think we're okay. I think we're okay. I kind of messed up. It was supposed to be a plus here. That's why these are coming out kind of weird. But I think we're okay. Let me double check. So that's going to be right. It's going to be negative. So then I bring the negative in front. So I have a negative there. That's negative. And then multiply by the derivative of that. So we're going to have a negative. I think we're good. Then we have the negative 1/2. That negative moves in front. That comes out to be positive times the negative. So we have another negative. So we're just going to have to deal with this. So we have the square root of 1 minus x. Weird things are going to have to happen here. So that's going to be f of 0 plus f prime of 0 times x plus f double prime 0, x squared over 2 factorial. And they wanted another term, f treble prime 0, x cubed over 3 factorial. So we're going to get 1 minus 1/2 x minus 1/4 x squared over 2 factorial plus 1/6. Okay, I messed up. Back up. Negative 3/8 minus 3/8 x cubed over 6. And so we're doing approximation. 1 minus 1/2 x minus 1/8 x squared. And that's going to be 3 is going to cancel even 2 minus x cubed over 16. And we're trying to approximate what? Square root of 1.15. So we're going to do minus negative 0.15 to get square root of 1 plus 0.15, or square root of 1.15. So I have to replace all these x's with negative 0.15. 1 minus 1/2 times negative 0.15 minus 1/8 negative 0.15 squared plus negative 0.15 cubed over 16. I'm not going to do that because I don't feel like it. Punch that in your calculator. You get your answer. And that's that. Okay, so that's example 4. And we're pretty much done. I'm just going to show you, these are some Mclaren series that you have to just memorize. This is the one we've been looking at the whole time, geometric. E to the x is pretty easy. 1 over 0 factorial. X over 1 factorial, x squared over 2 factorial, x cubed over 3 factorial. You see the pattern. Now, sine x is kind of like e to the x, except you only use every other term. You see that? Every other term. And they alternate signs. And then the cosine is like e to the x, but you only use every other term, but you alternate signs again. So you have to have those memorized. These are your basics that you need to have memorized. These actually all derive from here. So to get arctan, if you make this plus x squared, which you can simply do by replacing x with minus x squared, and then you integrate that, the integral of 1 plus x squared is arctan, so that's where that comes from. That's derivable. And this, if you integrate this, we'll first make it plus by replacing all x's with minus x. Then you integrate it, you're going to get ln of 1 plus x. So that's how you would get some of these, but these you don't have to memorize. It's the first 4 that are the biggies. If there's another one, I guess I'll have to point that out. And that's the end of the video.